Alright guys, welcome back. We're going to head towards complex numbers in this unit, and our goal is we're shooting towards vectors. So we're going to start out today with a quick review of complex numbers. Y'all have seen this back in Algebra 2. We just need a good quick refresher. So our complex number system, basically everything in math has came around because there's been a problem at one point and we've needed something to extend something that we've just learned. So when math basically started out, people started with counting with natural numbers. Those were numbers of 1, 2, 3, 4. Those are your basic counting numbers. And people used those number system for a while and then realized that, wait a minute, we need in addition to this didn't cover everything we needed. And then they came along and developed the whole number system. Now, the whole number system didn't really add much, but it added a big thing, 0. And so we still have all our counting numbers. They extended that. They put 0 in with it. After we've got started in 0 and went through all positive numbers, then we realized, wait a minute, we could do a little bit more to close basically and get closure with subtraction. We needed to add another system in, and that was the integer system. And integers are positive and negative whole numbers. So starting at negative infinity, all the way up through 0, and then all the way through positive infinity. Notice each one of these, basically I'm doing a Venn diagram here, and each number system completely contains the other up to this point. Whole numbers have all the natural numbers contained in them. The integers contain all whole and all natural. So these systems are just building out. We're just adding more as history went through and we realized we needed more numbers. Then, after they've dealt with integers for a while, they realize that, wow, there's things between 0 and 1, and those numbers we call rational numbers. And so we can actually break that in part. Now, these are your favorite types of numbers in math, and as far as most students are concerned, these are your fractions. And so this is a number that can be represented in the form a over b, where b is not 0. You can never have 0 in the denominator. And like I said, these are in between our integers. They can include the integers because that is inclusive in the set. All right, and then we went for a long time and we felt, all right, we've got numbers down now. We can solve any type of problem. And what came up next was there were numbers that started popping up, especially in geometry, that, wait a minute, we can't come up with a fraction for this. And that became our irrational system. And a good common one is square root 2, pi, the number e. All of those are irrational numbers that we couldn't express in the form of a fraction. Remember, the fractions also numbers that terminate or numbers that repeat, or numbers that we can get a pattern and basically get it into fraction form. These irrationals were numbers that we couldn't get to that form. There was no pattern. We looked and searched and went deeper and deeper and deeper. And that has pretty much got you through a lot of your basic math right there. These numbers did make up your real number system. Basically, at this point, we've had instances where we've had problems in something and we've had to develop something new. Well, in the same thing here, we had a problem with the real number system, and it didn't solve all cases we needed. And we brought in these numbers we're calling imaginary. Now, these numbers are not synthetic, they're not fake, that's just sort of what they were first named, but they helped us solve an additional case, the main one being square root of a negative number. And when you come across this in a problem, it's like x squared equals negative 5. In the real number system, there's no solution for that, but that came up in some problems. Square root of negative 1, we call that I. That is the imaginary unit. So that's a good thing to memorize, get in your head. Anytime you see a square root of negative 1, replace it with the I. So that'll be an imaginary unit. You can also have like negative 3i, 8i. There could be anything with the I, any coefficient basically. But that base number, that I, is the imaginary unit. This all together makes up the complex system, which is in the form a plus bi. The real numbers have 0 i's, so they're just the a part of the complex system. The pure imaginary have no a part, and they're just the bi part. But all that together makes up the complex number system. Now, all of our operations pretty much that we can do with regular numbers, we can do with complex numbers. Let's look at deriving a little bit. First, with simplifying some radicals and where these complex numbers, some of the cases they pop up. Let's say we take the square root of negative 8, and I can see that negative 8 would break into perfect squares of 4, negative 1, and root 2 is not the perfect square. And then we know, well, square root of 4 is 2. The square root of negative 1 we just learned was I. So we got our 2. Then we've got our I. And then the radical 2 won't simplify, so we're just going to leave it root 2. So that would be simplifying. Square root of negative 8 would simplify to 2I root 2. All right, if we come across one like square root of negative 16, we could break that apart into root 16 times root negative 1. And square root of 16 we know is 4. And square root of negative 1 is our I unit. Now, powers of I, this is handy to know as far as we're working through. I to the first power, that's going to be I. I squared, this is another great definition to know. If I equals the square root of negative 1, and we square root that, or we square that, that would mean I squared is just the negative 1. All right, if we try to find I cubed, that would be I squared times I, so we can go back to what they equal. That would be negative 1 times I, which is negative I. I to the fourth ends up being I squared times I squared. Well, that's negative 1 times negative 1, which is positive 1. All right, continuing this pattern on, I to the fifth would be I times I to the fourth. So that is I times 1, which is I. I to the sixth would be an I squared times I to the fourth. And we could pair these in any way that you want to, which just comes out to the negative 1. And I to the seventh would be I cubed times I to the fourth, which is negative I times 1, which is negative I. And I to the eighth is I to the fourth times I to the fourth. 1 times 1 would be 1. You notice these answers are repeating. They will continue to repeat no matter how high the power gets. So we always can break it into parts of like I squared, or we can factor it back down to these base parts and clean these up. So that's a good type of problem to be working with, is they'll just give us some random number I to the 50th power. We break that down into our pieces that we could. That would be I squared to the 25th. Well, I squared is negative 1. Negative 1 to an odd power would be negative 1. So we can simplify any I to any power pretty easily, breaking down to these base parts. All right, some other operations with them. Let's go to adding and subtracting complex numbers. So first type, let's add. So let's say one number is 3 plus 5i, and we're going to add to it a negative 2 plus 3i. Adding and subtracting complex numbers, really simple, really straightforward. You're essentially combining like terms. So looking at my a parts, the 3 plus the negative 2, I get 1. Then looking at the b component, 5i plus a 3i will give me the 8i, and there's my answer. So addition, basically it's just like combining like terms back in Algebra 1. All right, subtraction is really going to work the same way. So we're going to have 6 plus 4i minus 3 plus 6i. We look at our like terms there, our a's, 6, and then we're going to do minus 3 will be 3. And then we have a 4i minus a 6i. We'll put a minus 2i, and we've got it. Multiplying complex numbers. This is also going to be very familiar to algebra. So we have 5 plus 3i times 2 plus 7i. We need to distribute, basically. Some teachers will call this the FOIL method. I try to stay away from that. It's just like distributing. That works for any term or any size polynomials, essentially. So we need to take the 5, distribute it out to the 2. That gives me 10. Then take the 5, distribute it out to the 7i. I've got 35i. Then we'll go to the next component, that b part, the 3i, distribute it to the 2. That'll be a plus 6i, and distribute onto the other piece. That'll be plus 21i squared. Trying to simplify this and clean it up, we have 10 plus 41i plus 21, and in place of that I squared, I'm going to substitute what we just talked about the last page. I'm going to plug the negative 1 in there. And that would give me 21 times the negative 1 makes a minus 21. So I'll have 10 minus 21, which is negative 11, and then plus my 41i. So when you distribute and multiply complex numbers, you will distribute out. lots of times there will be an I squared. We always want to convert that. We don't want I to any higher power than 1. We can always convert it back to an I. And then combine like terms, clean it up. All right, reviewing some conjugate material. If z, the number z, is equal to a plus bi, and it's a complex number, then its conjugate is going to be written or denoted by z bar. So that's just a way of writing, one way I've seen people write this. And it's really going to be defined by, to get the conjugate of z bar is going to be equal to a plus bi bar, which all that really means to do is flip that sign in front of the imaginary term. So it's going to be a minus bi. The nice thing about this, and why we even are concerned with it, the product of z bar is always going to be a positive real number. So that's going to eliminate all imaginary units. Basically, thinking back to this is going to be very similar to our radical problems. So it's us trying to get rid of that. All right, and putting that to use, we're going to write a quotient in standard form. So we're going to have a division problem, and we're going to have 1 over 3 plus 4i. So we have the imaginary unit in the denominator. Remember, that's essentially like a radical in the denominator. To clean that up, and to get this just into a standard form, a plus bi form, I'm going to multiply the numerator and denominator by the conjugate. So there's my denominator, there's my numerator. Remember, I flipped the sign on the imaginary term. I'm going to distribute on the top. 1 times both will just give me 3 minus 4i. On the bottom, when I distribute, I'm going to get 9 and then minus 12i. Distribute the 4i would be plus 12i minus 16i squared. Some stuff that's going to clean up. The top's going to stay the same. On the bottom, the i's in the middle are going to cancel. I'm going to convert that I squared to the negative 1. So I really have 9 plus 16, which is 25. And that last little bullet I told you on the last page was, when we multiply a complex number with its conjugate, we always get a positive real number. And there we got it. Now, to clean this finally up in standard form, I need to distribute that 25 to both terms, essentially. So I'm going to write that as 3 over 25 minus 4 over 25i. That gets my real and my imaginary parts. So I'm really in that a plus bi form now. And that's the big point of this. All right, let's try another quotient property. Let's say we start out with 2 minus 3i over 4 minus 3i. I need to multiply by the conjugate of the denominator, so I'm going to multiply by a 4 plus 3i on top and bottom. Remember, we can do that because we're essentially multiplying by 1, and it's not changing the value. This one's not going to clean up as nice. On top, I'm going to have 8 plus 6i, and then minus 12i, and minus 9i squared. In my denominator, I'm going to have 16 plus 12i, minus 12i, minus 9i squared. I see on the bottom the middle terms cancel. The last one I convert to a negative 1. So that really makes it 16 plus 9 in my denominator, which will be 25. On top, it's not going to clean up as nice, but that's no big deal. I'm going to convert the I squared, and that will make 8 plus 9 will be 17. And then combine my other 6i minus 12i is going to be a minus 6i. So we've done our conjugate work. We've gotten rid of all imaginary units in the denominator, and we got to one number. That way we can put it underneath each one of the top. That will give me 17 over 25 minus a 6 over 25i. So we are truly in a plus bi form. All right, guys, hopefully this helped. This was a really quick refresher over complex numbers. When you did this back in Algebra 2, you probably spent a chapter of several days' work on this. So this is just a real brief overview. We can talk about it more in class. And if you have any questions, feel free to tweet me or leave me a comment. All right, thanks.